Hello, everyone. I'm Xionghui Yang from Peking University, and this is joint work with collaborators from Peking University and Tencent. I will present our work on distilling featherweight AI agents for mobile MOBA games. The main message is that mobile deployment for complex game agents should be handled by a Pareto-guided pipeline. In honor of King's 3v3, our final featherweight agent achieves a 40.32% win rate against the teacher, while delivering 12.4 times faster inference and 15.6 times better energy efficiency. Why is direct on-device MOBA deployment hard? In honor of King's 3v3, the state is a 13,758-dimensional multimodal observation, decomposed into 3 hero-specific observations of 4,586 dimensions each. The action space is hierarchical and has more than 22 million possible actions, with legality masks to restrict valid choices. At the same time, mobile deployment requires low latency, low energy use, small memory footprint, and compact model size. So the core tension is clear: strong policies want large heterogeneous networks, but mobile platforms demand fast, efficient inference. Our key idea is to ask a different question. Instead of asking for the smallest model, we ask which operating point best matches the device budget. We formulate deployment as a multi-objective optimization problem, where performance is measured by win rate, and efficiency includes latency, energy, memory, and model size. This gives an empirical Pareto frontier of non-dominated candidates. In practice, there is rarely one universally best model for all devices. Based on that view, we build an end-to-end Pareto-guided pipeline with 5 stages: architecture design, architecture search, distillation training, agent evaluation, and agent selection. We first profile the teacher and define a mobile-efficient student blueprint. Then we search candidate students under a constrained compute budget, distill each candidate from the teacher, evaluate both game performance and real device efficiency, and finally select a deployment-ready operating point. The key difference from standard compression is that this is a full deployment pipeline. It combines search, distillation, and real device evaluation, and uses Pareto-based selection instead of a single proxy metric. The student architecture is not chosen arbitrarily. We first profile the teacher and find a clear bottleneck pattern. The encoder accounts for 82.27% of flops, while the LSTM accounts for 51.11% of parameters. Together, they contribute 83.49% of computational cost and 80.5% of parameters. This motivates a lightweight student architecture for mobile deployment. We replace the expensive cross-modal and cross-temporal fusion modules with MLP-based alternatives, while preserving per-hero feature extraction and team coordination. We then run a closed loop over candidate students. The search space is built from 7 parameterized building blocks and is constrained to 1 to 20% of the teacher flops, with 20 compute intervals for coverage. Distillation uses teacher self-play data with 2.02 million state action transitions, split into 2 million for training and 20,000 for validation. The objective is the average KL divergence over 5 hierarchical action subdistributions. Finally, we evaluate real device behavior on an IQ0012 smartphone. The final featherweight agent is a balanced deployment point. It achieves a 40.32% win rate against the teacher, with 0.436 milliseconds latency, 0.49 mAh energy per game, and a 9.89 MB model size. Relative to the teacher, this corresponds to 12.4 times faster inference and 15.6 times better energy efficiency. The trade-off plot shows that our final model lies on the empirical Pareto frontier and satisfies the deployment constraints, including win rate above 40% and latency below 0.5 milliseconds. In contrast, standard post-hoc baselines are weaker trade-offs. Low-rank decomposition and quantization stay near 40% win rate but remain around 3 milliseconds, while pruning becomes fast but collapses to 3.27% win rate. The ablation study explains why this design matters. Adding back the LSTM changes win rate only slightly, but makes latency and energy worse. Restoring the original encoder raises win rate, but the device-side cost becomes too large for practical mobile deployment. Scaling the MLP up or down also gives inferior trade-offs around the selected point. Our final takeaway is that the proposed Pareto-guided pipeline is well suited for mobile deployment of complex MOBA agents, delivering a stronger performance efficiency trade-off than standard post-hoc compression baselines. Thank you.